Texas Lutheran University.
Andres De La Garza for our last presentation of the semester. We saved the best for last, right?
We saved the last for last.
So Andy's from Seguin, graduated from Seguin High School, though he's originally from
Boo, yes.
Illinois.
Mm-hmm.
And he will be going off to Texas State next year to get a master's
Maybe.
In physics, material
in
science.
physics, which I would minus him 1,000 for, but because it's material science, it's kind of like chemistry. So
Yeah, that's chemistry.
yeah, it's really
Physicists, they may call it. Physics was
but
chemistry.
it's actually chemistry.
Give me a break.
Anyway, he's going to talk to us about organic light emitting diodes.
All right, y'all ready? So,
ready.
can I turn these lights off?
Yeah.
Okay. So, like Dr. Bray said, I'll be presenting my research over organic light emitting diodes, also known as OLEDs. In the presentation, my outline, I'm going to start with history, move into applications, talk about unique properties of carbon, why we're using carbon instead of inorganic semiconducting materials, and then move into conductive properties of organic molecules. I want to talk about what makes them conductive. Then some important device parameters to keep in the backs of our minds to when we're developing these devices. And finally, some of the methods used to fabricate these devices, characterize, and I want to compare two types of OLEDs that are on the market today. And then I'll wrap up by just summarizing the main points of my presentation and say a couple words on the future of OLED technology. So before we get started, I want to I want to define a couple of things. So electroluminescence is the emission of light from a material that's been electrically excited. A semiconductor is a material that has the properties between that of an insulator and a conductor. Doping is the intentional addition of an impurity into a semiconducting material to modulate its electronic properties. P-type semiconducting material is a semiconducting material that's been doped with a electron deficient substance, making the bulk of the material deficient in electrons. And then an N-type is the opposite. You dope with an electron-rich substance, making the bulk of the material have an excess of electrons. And then P-N junction is you bring the two semiconducting materials together, and that interface between the P and the N forms that P-N junction. So now some history. In 1907, H.J. Round discovered electroluminescence in crystals of silicon carbide by applying 110 volts of alternating current through the crystal, and he would see little specks of light. Then in 1960, Martin Pope showed that you could drop those drive voltages by using single injection electrode contacts in crystals of anthracene. Then in 1965, Helfrich and Schneider showed that they could improve upon Pope's work by using double injection electrode contacts. And then in 1977, Schröckwa and some of his collaborators showed that by doping polyacetylene, they could modulate its conductive properties from that of an insulator all the way to the conductive properties of metals. And then finally, in 1987, Tang and Manslyk manufactured the world's first organic light emitting diode. So now I want to tell you guys about the differences between LEDs and OLEDs. So an LED uses an inorganic semiconducting material to emit light. And an organic light emitting diode uses electroluminescent organic molecules to produce the light. And some of the applications of these devices is in solid state lighting. You could have solid state lighting like you could have the lamps, you could have your phone camera, not your phone camera, the flashlight on the back of your phone, you could use it for that. You could also use them for display applications. As you can see by these figures, you can use them in your smart watch, your smartphone, televisions. And an interesting property of these OLEDs is that you can make them flexible. And that's not something you do with LCD displays. So some of the advantages of using OLEDs is they're thinner, they're lighter, they produce more vibrant colors and true blacks. Now, if you compare them to LCD displays, an LCD display uses a shutter, an LCD shutter array to to filter a white light source from a backlit display, backlight. And so because LCD displays have those components, they also need extra electronics to drive those components. Whereas OLEDs don't have that. So they consume less power because they don't need to drive those extra electronics. They have faster refresh rates, again, because they don't have that LCD shutter array. It's just a matter of switching on and off pixels. They have wider viewing angles, and because they lack all those extra electronics, they have a more simple construction, which is attractive to manufacturers because you don't have to, pay to make all that extra stuff. Now, some disadvantages of these devices is that they have a shorter lifespan than inorganic semiconductors, inorganic LEDs, and they degrade in the presence of oxygen and water. Should I do something about that?
Just click on the PowerPoint.
Sorry.
Click on the PowerPoint.
Okay. So now, why would we use organic molecules when they don't last as long as inorganic semiconducting materials? So just a couple of properties of carbon. It has a relatively small size, so when it's found in organic molecules, it's not as sterically hindered as other bigger molecules, and that makes it reactive. It also has an electronegativity between a lot of the known elements, so it likes to form covalent bonds. It has 4 total bonds in its valence shell, giving it a total of 4 bonds that it can form, and it can have single, double, and triple bonds. So that's just some general information about carbon. But the special thing about carbon is that it's found in lots of different structures. You could find, it's just an unimaginable amount of structures that you could have carbon molecules in. And that means that researchers can synthetically engineer these compounds to have very specific electrical, optical, and mechanical properties. So now, what is a diode? So it's a 2-terminal semiconducting device that restricts the flow of current to a single direction. And the way it does that is, if you remember me talking about that p-n junction, so at that p-n junction, the excess charge carriers neutralize one another, forming a non-conductive region. But when you place a voltage across that device, with positive terminal connected to the p-type, negative terminal to the n-type, what you're doing is you're stripping more electrons from the p-type, injecting holes, and which is the absence of electrons, and you're injecting electrons into the n-type. And we know that like charges repel one another, so what's going to happen is that you're going to push those electrons closer to that p-n junction, and you're going to push those holes closer to that p-n junction, and what you'll have is a hopping, electrons hopping from the n to the p, and holes being left in the n, and that process will continue, and you'll have a flow of current. Now, if you reverse the poles of a voltage, of that voltage supply, what you'll get is you'll have holes being introduced into the n-type and electrons being introduced into the p-type. So we know that opposite charge carriers attract one another. So what you have is a widening in that depletion region. And like I said, it's non-conductive, so no current passes. That's called reverse bias. And this is forward bias. So here's just a current voltage characteristic curve of a diode. You see with enough voltage in the forward bias direction, you have a flow of current. And also you will have a flow of current with enough reverse bias voltage, but you risk electrically breaking down the device. So now I want to talk about conductors. So when we think about conductors, we typically think about metals. And the reason metals are good conductors is because the electrons in their valence shells are delocalized. And what that means is that they can move from atom to atom within the crystal structure of the metal. But when we think about organic molecules, at least when I think about organic molecules prior to this research experience, I didn't think of them as being conductors. But there exists a specific type of organic molecule called a conjugated molecule that does exhibit semiconducting properties. But before I get into that, I want to talk about the hybridization state of that molecule. So for those of you who don't remember what hybridization is, it's just the mixing of atomic orbitals to produce molecular orbitals. And this concept explains the geometry and bond angles in a lot of molecules. So the hybridization state that of interest to this study is sp2 hybridized carbon. And in sp2 hybridized carbon, what you do is, or what's said is done, you promote a 2s electron into a vacant 2p orbital, and you mix one 2s with two 2p orbitals, forming three sp2 hybrid orbitals, coplanar, oriented 120 degrees from one another, and you have left over a singly occupied p orbital. So in conjugated organic molecules, the backbones of these molecules are sp2 hybridized. And you have these singly occupied p orbitals, in the case of benzene, that can form pi bonds and break apart and form pi bonds with neighboring molecules, effectively delocalizing the charge above and below the plane of the molecule. So that gives these molecules their conductive properties, the ability of having those electrons be able to move from atom to atom in the molecules. Same thing for polyacetylene. It has that structure, single, double, single, double, single, double bond. You could break those pi bonds and reform them with neighboring p orbitals, and you'll have the delocalization of electrons, giving it its conductive properties. So now, like we just talked about, you have two sp2 hybrid orbitals that come together, and they form a sigma bond and a pi bond. They actually form a pi bonding orbital and a pi anti-bonding orbital, lower and higher in energy than the original two orbitals. And now if we were just to consider an infinitely long conjugated molecule, such as, say, polyacetylene, that just went on forever, then what we would get is this quasi-continuous continuous energy band through a process called splitting. You'd have multiple bonding pi orbitals of different energies and multiple anti-bonding orbitals of different energies. So you have a region where electrons can populate here, here, but not in between. In the ground state, the highest orbital, molecular orbital in energy that has a pair of electrons is called the highest occupied molecular orbital. And the anti-bonding orbital directly above that, with no electrons in it, is called the lowest unoccupied orbital. Now, the difference in energy between these two frontier orbitals gives these molecules their conductive properties. So if that gap is too big, then it's going to be hard for those electrons to move from the HOMO into the LUMO. And if that gap is overlapping, then it's going to be really easy for those electrons to transition from the HOMO and the LUMO. So, sorry, I didn't say what the first one was. So if it's really big, it's an insulator. If it's overlapping, conductor. And if it's somewhere in between, then it's a semiconducting material. And that's similar to the valence and conduction band of inorganic semiconducting materials. So now I want to move on to the important processes that happen within these devices. So the first one is going to be charge injection at the electrodes. Next, charge transport through the organic materials. And finally, electron-hole recombination and the emission of light in the device. So charge injection, what charge injection is either the overcoming or tunneling through a potential barrier. The charge carriers either overcome or tunnel through the potential barriers. And the potential barriers are formed at the interface between an electrode and an organic material. So I'll be using this ITO PPV aluminum energy band diagram for a PLED. What a PLED is just a polymer light emitting diode. It's another class of OLED. And for any of you who don't know what ITO is, it's just indium tin oxide, and it's a transparent conductive material used used often in OLEDs. And PPV is this molecule right here, polyp-phenylvinylate. So to inject a hole into, from the anode, this ITO anode, into the highest occupied molecular orbital of the PPV, you need to overcome the hole injection barrier, which is defined as the difference between the work function of the ITO and the ionization potential of the PPV layer. So what a work function is just the minimum amount of energy needed to remove an electron from the surface of the ITO and put it into the vacuum region. And an ionization potential is similar to that, but it's taking an electron from the highest occupied molecular orbital and putting it into a vacuum region. On the other side, the potential barrier needed to be overcome or tunneled through for an electron to be injected into the lowest unoccupied molecular orbital is defined as the difference between the work function of aluminum and the electron affinity of PPV. And what an electron affinity is just the minimum amount of energy needed to take an electron from the vacuum region and put it in the LUMO level. So now charge transport. So charge transport in metals is typically thought to happen through drift and diffusion currents because of the high degree, the structure of those metals is it's very structured. Those metals are very structured. So what drift currents are is the movement of charge carriers through a material by the force applied on them by an electric field. Diffusion currents, on the other hand, are the movement of charge carriers, the random movement of charge carriers from a region of high density to a region of low density, as you can see here. They're packed, and then they're a little more spaced out. But we can't really say that's what happens inside of organic semiconducting materials because they have very weak intermolecular forces, the van der Waals forces. So they're very disordered. They're all over the place. And due to those large intermolecular, due to those small intermolecular forces, there's large intermolecular distances between them relative to the electrons. And that leads to very small intermolecular orbital overlap, which leads to the charge mobilities being very low in these materials. So the model that's used to describe how these charges move from molecule to molecule in these semiconducting organic molecules is called the hopping transport model. And it says just with enough energy added to these electrons, they'll hop from molecule through space and hit another localized they'll jump from molecule to molecule, and you'll have your flow of current. Now that we've talked about the injection of charges and the transport of those charges, what's left to happen is the electron-hole recombination. So I'll be explaining electron-hole recombination using this diagram here. And I want you guys to think of the S naught, the ground state, as the HOMO level, and these first two excited states as the lowest, the LUMO level. So one of the transitions that you could have is a singlet to ground. It's called fluorescence, and those are typically very fast transitions. Another one is a singlet to triplet intersystem crossing. The spin of the electron flips, and it moves from a singlet to a triplet. Another one is from triplet to ground. So you have this triplet to ground, which produces phosphorescence, and those are a little slower. And then you have non-radiative transitions where the energy, the excited energy of those electrons is lost to like collisions with other molecules, and it's lost through vibrational, rotational, or translational energy, also known as heat. So now that we know how the charges move throughout these materials, I want to talk about the function of layers that make up these devices. So modern devices use a couple layers to facilitate the injection and transport through the device. And I'm going to start at the cathode. make my way down to the emissive layer, and then go over to the anode and make my way up into emissive layer. So the cathode is the negatively charged electrode, and it's the source of electrons. So from the cathode follows the electron injection layer. What the electron injection layer does, it facilitates the injection of charges from the cathode into the organic layers. Then from the injection layer, you have the electron transport layer, which just helps those charges move from the injection layer into the lowest unoccupied molecular orbital of the, lowest unoccupied molecular orbital of the emissive layer. And now the anode is the positively charged electrode, the source of holes, and on top of it, you have the hole injection layer. What the hole injection layer is it just facilitates the injection of charge carriers from the anode into the organic layers. And then you have the hole transport layer, which just facilitates the movement of those charge carriers up into the highest occupied molecular orbital of the emissive layer. Then once we have a hole and electron pair in the emissive layer, we could have any one of those four recombinations that we talked about on the previous slide. So the most common ways these thin layers of organic molecules are made is either through spin coating, chemical vapor deposition and spin coating. So what chemical vapor deposition is you have your system under vacuum, as shown by this bulb right here. It's like that system's under a vacuum, and you have your molecule of interest that you want to deposit in this little evaporator. You heat that evaporator and you vaporize those molecules, and they condense onto the surface of your substrate, forming a thin uniform layer of your organic material. On the other hand, we have spin coating. You take the molecule that you want to deposit on your substrate, you dissolve it in a suitable solvent, and deposit it on the substrate, spin it down, and that forms that spreads that layer thin, that organic layer thin, and as you're spinning it, it evaporates the solvent and leaves just a thin layer of the organic molecule. So after we've made those layers, all the layers we needed to put on the OLED, we have to characterize these devices. And the way we do that is by using a source meter and an integration sphere together. So what the source meter does is it passes a voltage through the device, and it reads the current that's being used to light the device. An integration sphere, so our device is inside an integration sphere, and it's emitting its light, and what the integration sphere does, it just collects all that light and transports it through a little exit hole that's connected to like a UV vis spectrometer, and it reads the light intensity as well as the wavelength emitted. So from that data that we could collect, we could calculate the efficiencies. The external quantum efficiency is the ratio of how many photons exit the device to how many electrons are injected into the device. The power efficiency is the ratio of how bright the device is to the current density needed to drive that device. And then the luminous efficiency is how much of that light is passing through the device as a ratio to the electrical power needed to drive that device. So these two are given in candelas per amp and lumens per watt. So now that we kind of know how these devices work, I want to talk about two types of devices. There's fluorescent OLEDs and phosphorescent OLEDs. So this schematic diagram is showing the process that occurs in a fluorescence OLED. So quantum mechanics says you have 25% of the excited electrons in the singlet state and 75% in the triplet state. But in a fluorescence OLED, the singlet and triplet don't mix. So what you have is all radiative decay from singlet to ground, and you'll have a lot of quenching, or just the loss of loss of energy from the triplet to heat. So you're losing most of the energy you're putting into the device through non-radiative decays. On the other hand, the phosphorescent OLED uses a heavy metal atom in the emissive layer to produce spin-orbit coupling, which means that the S can now interact with the T. And like we said, we had 25% in the S and 75% in the T. So what that metal does, it facilitates the transfer of excited electrons from S to T and then down to ground, producing phosphorescence. Now I just want to compare two devices, one fluorescent and one phosphorescent, and I want to show you guys the difference between the two. So in my literature research, I found this green phosphorescent OLED to be, they said it was highly efficient. It has a triple layer structure that you can see right here. So it has an ITO coated glass substrate followed by MPB whole transport layer. That's this molecule right here. And then next up you have the emissive layer doped with what they call C545T. And what that molecule was used for was to trap the charge carriers in the emissive layer and help it have radiative recombinations. And then on top of that, you have an electron transport layer called DBZA. That's that molecule right there. And up here, you just have the energy bands. So all these are the HOMO energy levels, and those are the LUMO energy levels. And now, looking at the specs of this OLED, we have an external quantum efficiency of about 10, brightness about 23,000 or 24,000 candelas per meter squared, and power and luminous efficiency of about 30. Now, let's compare that to phosphorescent OLED. So, like I said, phosphorescent OLEDs have a metal atom in the emissive. They have a metal atom in the emissive layer that gives rise to that spin-orbit coupling that I was talking about. So again, we have a triple layer structure, the ITO-coated glass substrate followed by the TAPC whole transport layer, and then the metal complex doped with MCP, which serves the same function as the other dopant. It just captures charges in that emissive layer and forces them to recombine. And on top of that, you have the TPBI layer, electron transport layer, and lithium fluoride and aluminum cathode. So last time we had 9% EQE and about 30% for the power efficiency and luminous efficiencies. So we see that both of these have gone up, as well as brightness. So you have a brightness of about 64,000, which is about 3 times as much as the fluorescence OLED. That just shows us that the phosphorescent OLED is more efficient in producing light. And that just leads me to my summary. So, like we said, these OLEDs can be used for solid state lighting. They could also be used for display applications. We talked about how organic molecules, conjugated organic molecules have semiconducting properties. We talked about the layers and their function and how the layers are deposited on a substrate. And with the proper choice of proper architecture of the device and proper choice of organic materials, you could have very highly efficient OLEDs. And so, like I just showed you guys, fluorescent OLEDs are probably not what will be looked into more in the future. We'll probably be looking more into phosphorescent OLEDs and trying to bring up the efficiencies of those devices. So I'd just like to thank the chemistry department, my family, my friends, and if y'all have any questions, please feel free to ask.
Student questions? And student questions? Thanks, Mara.
You said that the organic molecules have a shorter lifespan
Mm-hmm.
than the inorganic ones. how much shorter is it? Is it like half the life of it? Is it a quarter or what?
It depends, because so the biggest issue right now with OLED TVs is that the blue OLEDs, the blue emissive layers, degrade really fast, whereas the red and green they kind of, I mean, they're not as good as inorganic semiconducting materials, but I don't have an exact number. I just know that blue degrades a lot faster than the other three, because you have RGB to make white light. I don't know exactly what lifetime is on these devices, but I know that blue degrades faster than the other three colors.
So you can
Sorry.
You can buy these already?
Yeah.
Can I, this is a follow-up. Why? Why does blue degrade faster than the other ones?
That's a good question.
Postulate that. Even if you don't know the answer to that, you can probably think about that.
I would think because, You go ahead.
You can't answer. It's his seminar.
I would think because blues, so blue would be a bigger excitation, right? You need more energy to excite electrons
Yeah, okay.
into.
This has anything to do with the excitation, but it might have something to do with the energy.
Well, what I'm getting to is that because you're having to put in more energy, there's more chance of having reactions at the interface between organic layers, and once you start having those reactions at the interface, that may compromise the charge transport that occurs between layers.
Is blue light short or long wavelength?
It's a shorter wavelength than
What in terms of energy?
is higher in energy.
You can't answer his question.
He was answering it already.
Well, but what's that have to do with
We're gonna have Vanessa step outside. Something that's constantly absorbing blue light will probably degrade faster than something that's absorbing and emitting a different wavelength.
Yeah, that's true. Yeah.
Good question.
That was a good.
Thanks for the follow-up, too. Next time I'm gonna prod you.
Are these TVs really expensive? Like, would you buy them?
Right now they are. Yeah, right now they're really expensive. But it's just because it's new technology. But like I said, since they don't have those LCD shutter arrays or the backlight to filter the white light and give us our colored images on our screen, it's just a matter of producing pixels, or having these like pixel matrices. You don't have to have like all those extra electronics that run the devices.
You may have like really super
Mm-hmm. Yeah.
Wait, no, I actually have a question. So does that mean, because like I know some TVs, like if you leave them on for too long, they'll like the screen, like it'll start to, like even when you turn off the TV, you'll still see like that.
Oh yeah, imprinting.
Yeah.
So yeah, that's a real big problem with OLEDs, and that's just because they degrade faster. So like you're saying, you'll still see the image afterwards. That's due to that's a big problem with OLEDs, that they just degrade and they leave the image on screen.
So doesn't that happen with like regular TV, like not OLED TVs right now too?
I'm not exactly sure. I just know that's a really big problem with OLED TVs because they degrade faster.
So they
than,
wouldn't be good for like. Okay, never mind. Yeah. I don't.
you could ask.
I don't have any more questions. Okay, just tell me now.
For more information, please visit tlu.edu.